When we first look at the cargo systems involved in the handling of liquefied gases, they look rather complicated. But if you get an understanding of the basic physics involved, then the picture becomes much clearer. What I intend to do in this talk is to go through the basic physics and show how these principles are applied to the cargo handling systems, and then to show a little bit of the engineering, how the systems are put together, and how the cargo influences their operation. First, we have to look into the properties of gases. These were investigated intensively at the beginning of the 19th century, and one of the first experiments was done by the physicist Boyle, who compared the volume of a gas and he varied the pressure on it. During these experiments, he held the temperature constant. Now, Boyle found that when the pressure was doubled, the volume was halved. The French physicist Charles then conducted a parallel experiment. He wanted to see how the volume of a gas varied at constant pressure, but with temperature increasing or decreasing. What Charles found was that as the temperature of the gas increased at constant pressure, its volume increased uniformly. So he got a straight line relationship. This in itself was very interesting, but led to a very important extrapolation. Because when physicists see a straight line, they want to start to see what happens if you extend this straight line. And when Charles's experiments were repeated for a variety of different gases, it was found that within experimental limits, the straight line extrapolated down and showed zero volume at approximately the same temperature. And this gave physicists a great insight into what was actually going on, because it's a strange result that if you cool a gas down and down and down, then suddenly at some point its volume goes to nothing. This point on the temperature scale, incidentally, was called the absolute zero of temperature, and the scale was named in honour of the great physicist Lord Kelvin, and this temperature point is given the origin point of 0 Kelvin. The Kelvin scale has the same interval degrees as the degree Celsius, but the 0 point is 273 degrees below 0 Celsius. And very strange phenomena occur at this level. But what is happening is that the volume of the gas is contracting. The atoms are coming closer and closer together. The atoms join together to make liquid and then solid. Let's think about a gas. A gas is a collection of molecules flying around in space. If you actually add up the volume of each individual molecule, it is quite insufficient to fill the space which contains them. We can think of gas molecules as billiard balls bouncing off each other. As we cool them down, the speed of movement decreases and they stick together and they become liquid. Now, a liquid is again bounded by the lower surfaces of its container, but the upper surface reflects gravitational attraction. Cooled still further, the molecules stick together more closely and form a solid. This has completely self-contained boundaries. It is self-defining. So it is not surprising then that when we condense a volume of gas and make it into a liquid, then we reduce its volume many hundreds of times. And this, of course, is the basis of transporting gases in liquid form. As a result of the work done by the early physicists about the properties of gases, it was possible to put together a number of different gas laws, as we call them. The first one, after the work of Robert Boyle, is the relationship between pressure and volume if the gas is held at constant temperature. This is called Boyle's law. And it shows that pressure multiplied by volume is a constant. The work of Charles related volume to temperature and showed that volume divided by temperature is a constant if pressure is held constant. The pressure law, named after no one in particular, relates pressure to temperature if the gas is held at constant volume. Now, with 3 variables and 3 equations, it's possible to make a general statement. But there was another physicist in the early 19th century who made a really amazing leap forward in understanding. The gentleman called Professor Avogadro proposed the hypothesis that we could relate volume to mass. What he found was that if you standardize temperature and pressure, and he chose conditions which he calls normal temperature and pressure, which is 0 degrees Celsius and 1 standard atmosphere, then he found for a variety of gases the volume of 22.4 litres held a quantity of that gas equivalent to its molecular weight expressed in grams. For example, if we're talking about methane, we're talking about 16 grams. For propane, approximately 44 grams. This has the same volume at NTP conditions. Avogadro took this hypothesis one stage further. He suggested that this volume of gas, which he called a mole, he said this contained the same number of atoms or molecules, irrespective of whether it was methane, propane, neon, argon, helium, whatever. He proposed that a mole of gas contained an incredibly high number. It's 6.023 with 23 zeros after it. And that hypothesis has been accepted as the basis of our physics to this day. So, with Avogadro linking volume to mass, this then gives us an insight, of course, into density, but by further substitution in the pressure laws, the Charles's law and Boyle's law, we can then derive a general gas equation which relates pressure, volume, the number of moles, or the mass, if you like, of gas present to its temperature by what is called the universal gas constant. And this is called a general gas equation. Dalton, another important early scientist in the development of modern chemical and physics theory, found out something else which is very interesting. He found that if you took a mixture of gases which did not react with each other chemically, then the pressure they exerted in a closed container was independent of the mixture of the gases. In other words, they behaved as though the other components of the mix were not present. We can picture this as billiard balls of different colours or sizes bouncing around on a billiard table. You can think of it qualitatively as if the atoms were so tiny compared with the volume that the differences between them made no difference. So Dalton's law states that the partial pressure exerted by the molecules of one component of a mixture are additive with the partial pressure exerted by the other components of the mixture, as if the other components were not present, and this makes the total pressure exerted. Let's think about pressure itself. If we think about it in simple terms, it is the force generated as the molecule of gas hits the wall of the container. We know that the molecules are incredibly light in mass terms. They're very, very small, very light. Therefore, they must be travelling very quickly. They bounce off the wall, and the change of momentum imparts a force. After all, at atmospheric pressure, each square centimetre of a surface in this room is receiving molecular collisions which impart a force of 1 kilogram for every square centimetre. This, of course, is balanced by the forces underneath the surface, the other side. But when we do pressure calculations, it is important to realise that in general industrial practice, we are measuring pressures relative to atmospheric, whereas in scientific terms, we must take them on an absolute basis. In other words, we take gauge pressures to show the pressures above atmospheric pressure, but in our gas law calculations, we must always allow for the fact that there is 1 atmosphere extra pressure. This is the so-called absolute units of pressure. Now I wish to move on to the different phases of matter and what happens when a liquid is heated up and boiled or is cooled down and solidified. If we take water and we cool it down below 0 Celsius, it solidifies to form ice, and that is the form of water that exists right down to minus 273 degrees Celsius. So if we start with a block of ice, and if we heat it up at a constant rate, then as we add heat to it, we are able to sense the rise in temperature of that block of ice by means of a thermometer. We call this sensible heat, heat that can be sensed. But when we reach 0 degrees Celsius, although our rate of heating is constant, and there's no difference, there's no loss of heat from the ice block, we find that the temperature does not increase. So something is taking up that energy that we're putting in. And what's actually happening is that the molecules of ice are being split apart to make the more fluid, loosely bonded form, which we call water. And that destructuring, that breaking of these bonds between the molecules is absorbing energy. This heat is hidden, we can't sense it, so we call it latent heat. And because it's melting, it's called the latent heat of fusion. Now, we heat water up from 0 degrees Celsius up at atmospheric pressure to 100 degrees Celsius, and the molecules, they're increasing in their movement all the time. We can sense this heat again by thermometer. Again, this is called sensible heat. And then at 100 degrees Celsius, the molecules start to fly off into the space above the liquid surface. This we call boiling. Again, energy is needed to tear the molecules apart. There is an attraction, an interaction between the liquid molecules that has to be overcome before the molecules can separate into a gas. And this is called Again, latent heat, but this time the latent heat of evaporation. And this latent heat, the vaporization latent heat, is of great importance in our industry. Once the molecules of water in the gaseous form, steam, are away from the liquid, it's all converted, then the gas itself can be heated up, and this is known as the superheated gas. When the gas is in equilibrium with the liquid, we call that gas saturated. So these are the three phases of matter, as we call them: solid, liquid, and gas, and between them we have the latent heats. The latent heat of vaporization will become very important. Now, as we heat up, particularly the liquid, the heat absorbed versus the temperature rise are related directly in terms of what we call the specific heat of the liquid. But once we get into the gaseous form, things become a little bit more complicated, because we have to make allowance for the pressure energy. It's not just the temperature, we have to allow for the pressure. So rather than simply talk about the temperature of the gas, we talk about its total heat content. So we're allowing between the temperature and its pressure and volume. And this is called its enthalpy. I talked about the transformation of water from ice through water to steam, and at atmospheric pressure, the temperature points of these transformations are defined to give us the 0 and 100 of the Celsius scale. But we know if we alter our pressure conditions that we can vary this boiling temperature. On a ship we commonly do this by reducing the pressure, and we can boil seawater to distill it to make fresh water at jacket water temperatures. This is an example of pressure reduction, lowering the boiling point. Conversely, if you want to suppress boiling and raise the boiling temperature, you then increase the pressure. This is very commonly done, for example, in steam boilers or in autoclaves, domestic pressure cookers. In the radiator of your car, you have a pressure cap. This suppresses the boiling, raises the boiling temperature. Now, the total energy required to take the molecules apart is the same, but the conditions are varying. So it's not surprising that the latent heat of vaporization actually varies depending whether you're doing this boiling, this phase change, at reduced or increased pressure. So we can prepare a series of lines to show the boiling conditions at varying pressure. And this we do very commonly in our industry. We call these representations where we plot enthalpy, total heat, against pressure. We call these Mollier charts, and they can give us a profound insight into the process that we are dealing with in liquefying or condensing our cargo gases. To just have a quick look at the Mollier chart to get the general layout. On this axis, we see the pressure increasing. Because this is a scientific chart, the pressure is always written in absolute units. The enthalpy is shown along this axis. Enthalpy is a relative term. We talk about changes in enthalpy, so the 0 point may vary from one chart to another. It doesn't really matter. It's not an absolute scale. So what we measure is changes in enthalpy. And what we see here, we have the line of saturated liquid, and here we have the line of saturated vapor, and the lines between them, these represent the latent heat of vaporization. To this side of the line, this is the liquid subcooled going down towards freezing. And here we have the superheated vapour. Very interesting to note that the two lines join at a point here at a certain temperature and pressure, and this is called critical point. And now we can understand what really happens here. You see, if the atoms are flying around too fast, they will bounce off each other rather than being stuck together as we increase the pressure. As we slow the speed down, as we reduce the temperature of the gas, then the atoms will stick together and transform from vapour to liquid. So at temperatures above this certain point, you cannot liquefy a gas by just increasing its pressure. You must reduce its temperature below this point, then you can liquefy it. This is called critical temperature, critical pressure, and it's very important in certain aspects of our business. Because, for example, we have critical pressures, critical temperatures in the ambient range for gases like ethylene and ethane and even carbon dioxide. So this is a commonly experienced phenomenon. Here we show the phases of matter on the Mollier chart. Here we have the liquid, here we have the vapour, and in between we have a mixture of liquid and vapour. Lines show how much vapour and how much liquid. These are called dryness factors. Above critical point, the vapour is correctly called a gas. Below critical point, it is a vapour. It's a scientific detail. In practice, we use the terms interchangeably. So I certainly do. To complete our understanding of how we apply our principles of physics to the cargo system of a liquid gas carrier, we need to understand some of the laws of thermodynamics. There are basically 4 laws, but we only need to really look at the first 3. And the first one was actually such a basic principle that it was enunciated after the other 3 had been written. Therefore, they called it the 0th law rather than renumber the others. And the 0th law of thermodynamics, stated generally, is that if a body A is in a thermal equilibrium with body B, and body B is in thermal equilibrium with body C, then A and C are in thermal equilibrium with each other. This introduces the concept of thermal equilibrium between independent bodies. The first law of thermodynamics is very fundamental, and it is attributed to a Frenchman, Carnot, who noticed that when machining the barrels of cannons, that the metal heated up. Now his theory, which was proved incorrect, was that the metal contained corpuscles of heat which were ruptured and released when the machining bar, the boring tool, went down the barrel of the cannon. But what he did do was introduce the concept that mechanical work and heat were interrelated. And we still today study Carnot's theory as applied to the cycle of combustion, say for example in a diesel engine or in some sort of process, cyclical process. The second law of thermodynamics can be stated very simply. It states that heat flows from a hot body to a cold one. The more general statement is attributed to Lord Kelvin, which is that heat will not flow from a cold body to a hot one without external mechanical assistance. But this introduces the concept that heat flows in a certain direction, rather like electrical current. So these are the basic principles of the laws of thermodynamics. Now let us see how we can apply our gas laws and our laws of thermodynamics to the machinery installed on board a liquefied gas ship. In our cargo tank, let us say we have a cold liquid. The cargo tank is insulated. The insulation stops heat from the outside flowing in to the cargo liquid. No insulation is perfect, so some heat will come through. This is a consequence of the second law of thermodynamics. Heat coming in will overcome the latent heat of vaporization and will cause some of the cargo vapor to boil off, raising the pressure of the cargo tank. If we take this excess vapor now into a mechanical compressor, we then remove this vapor. We then perform mechanical work in the compressor, applying now Carnot's theory, the first law of thermodynamics, and we raise its temperature. This is an important step because in the cargo tank, the vapor might very well be quite cold. So we want to raise its temperature so that we can then cool it down with, for example, seawater. So again, we've got to raise it above the temperature of the cooling medium we're using so that we can apply the second law of thermodynamics. By cooling this hot gas with seawater, we then remove heat, we get the molecules slowing down, joining together, we take away the latent heat and we condense it. Now, in the condenser, the condensed cargo vapor is under pressure. The physicists Joule and Thomson, in a series of experiments 150 or so years ago, noticed that if liquid expanded from a high pressure to a low pressure, then partial evaporation caused the temperature of the bulk liquid to drop down. And this simple expansion is what we use to reduce the warm condensate liquid back down to tank temperature, tank pressure. It causes a partial evaporation, but this produces cold condensate to return to the tank. So the heat that was flowing in from the environment is rejected together with the additional work done by the compressor. It's rejected to the environment through the, in this case, the seawater. Now, we can show this very clearly on the Mollier chart. If we follow this through, we have boiling liquid at the tank dome. The gas picks up a certain amount of heat inevitably on its transit to the compressor. It is then raised in temperature and pressure by the mechanical work of the compressor. It is then cooled and condensed so it becomes saturated liquid in the condenser, and it is then expanded back down to cold liquid with a certain proportion of vapor and returned back to the cargo tank. This is nothing more than the simple cycle of the domestic refrigerator. We're applying this to our reliquefaction system, as we call it, using the cargo boil-off as the working fluid. Now, there are a number of points that we must take into account when we look into this in reality. Very few cargoes are what I would call chemically pure. Propylene in the polymer grade perhaps, certainly ammonia. But most of the commercial cargoes we carry, particularly for example LPGs, they are actually a mixture of some propane, butane, ethane in varying proportions. As we know from Dalton's law, the pressures are additive. But it is also common experience that the lower boiling fractions evaporate preferentially. So, as we can see here for this chart of propane and ethane, as little as 4% of ethane in the liquid phase, if we follow up to the lines, shows that our vapor composition contains 22% of ethane, 78% propane. This affects the mass flow through the compressors considerably, and as the cooling performance of the system is dependent on mass flow rate, then increasing proportions of ethane effectively reduce our plant cooling capacity. So a knowledge of cargo composition can give us an understanding of variations in plant performance. One other key factor in the performance of our plant is seawater temperature for the direct simple system. When seawater temperature rises too high, for example if we're in tropical or high temperature seawater areas, then the compressor has to raise the pressure from cargo tank pressure, which may be very low, through to the equivalent of condensation at seawater temperature, which varies of course with the cargo. This increases the compression ratio across the machine. So it may be that with low cargo pressure and high seawater temperature, that the cycle is more efficient by splitting the compression into two stages, and this is very commonly seen. Here, the principle is the same as before. The vapor is compressed, passes to the second stage, compression, and is condensed. It may be necessary to cool the suction of the second stage by putting a little bit of cool liquid into the second stage. This is normally only necessary when the cargo temperature out of the first stage becomes excessive, and basically you're running into problems with mechanical problems with the compressor valves. But the principle of two-stage compression is just the same. We condense the liquid, we return it back to the tank, maybe through an intercooler, maybe not, and we're rejecting the heat that passes through the insulation overboard with the seawater. And the cycle is as shown here on the Mollier chart. We're compressing it in the first stage. Here we're showing the intercooler at work. It is essential not to cool the second stage gas too far, otherwise you start putting liquid into the second stage. The second stage compresses it again to a pressure which depends on seawater conditions. We then expand the liquid down to tank pressure. Any liquid, of course, evaporating in the interstage cooler continues round in the cycle internally and effectively is like ballast, thereby reducing capacity a little bit. The purpose is, as I explained, to try and reduce valve temperature. If you look at a graph of valve performance of a typical compressor against pressure ratio, you will see that as you raise the compression ratio, the valves become less and less efficient. This is why two-stage cooling may be necessary when we come into high seawater, high condensation temperatures. Now, it is not necessary to use seawater for condensation directly. It is possible to use an intermediate refrigerant. This then, by correct choice of the refrigerant material, R22 is a very common one at the moment, but by correct choice of the condensation material, we reduce the pressure gradient across the first stage compressor, and we actually do the work of rejecting the heat in the cooling circuit, and this is called the cascade cycle. Here we're showing the hot gas from the cargo compressor evaporating the refrigerant, which is in itself in a closed cycle. The refrigerant is again condensed by seawater and returned back round to the evaporator. So we're balancing these two cascading circuits and cooling the cargo. This type of equipment obviously has more machinery, it's more complicated, but it's necessary for cargoes where critical temperature is above the seawater conditions in certain areas. This could be, for example, ethylene or ethane. R22 refrigerant-cooled cycles are used on many ships. It is a matter of the designer's choice. But if you have one of these on your vessel, then the Mollier charts again can be applied. You have a Mollier chart for the cargo cycle, and you have a Mollier chart for the refrigerant cycle. Likewise, our various cargoes exhibit the same sort of behavior. The boiling point at atmospheric pressure varies virtually in accordance with molecular weight. Let's take, for example, butane. At atmospheric pressure, the boiling point is approximately 0 degrees Celsius. If we raise the pressure up to about, say, 3 bar, we see the boiling temperature rising to approximately 35 Celsius. If we go to propane, for example, we see the atmospheric boiling temperature of about minus 42 Celsius. If we go up to a pressure of about 4.5 bar absolute, or 3.5 gauge, we see the boiling temperature is about 0. We normally work in maximum temperature assumptions of 32 degrees for seawater and plus 45 degrees C for ambient air. So we can see that up to temperatures of about 45, propane-propylene cargoes exhibit a pressure of about 18 bar gauge, which means we can carry them liquid in pressure vessels, those temperatures. If we look at the other cargoes, ethane, ethylene and methane, these are above their critical temperatures at these high ambients, so they must always be cooled down below critical to liquefy them. In practice, these more volatile cargoes are always transported cryogenic at atmospheric pressure. In the case of ethylene, about minus 104, methane, about minus 160. And this relationship between the pressure and temperature, the saturated liquid line, gives us the understanding of why this is, especially when we look at our critical temperature conditions. Now, because our commercial cargoes are actually mostly mixtures, we see some peculiar physical properties exhibited as a result of this. And one of them is the question of evaporation. If we leave a certain quantity of cargo in a tank after the end of discharge, we call this a heel. It's used to keep the cargo tank cool, or on an LNG tanker, it's used for fuel during the ballast voyage. Now, if this vapor is drawn off, particularly on an LNG tanker, and natural vaporization is used, the most volatile components are drawn off first, which means the composition of the heel that is left behind varies. It increases in what we call the heavier ends as we take off the lighter components. If you wish to avoid this happening, what you must do is evaporate a quantity of liquid simultaneously by pumping the liquid into a heat exchanger and evaporating it all in one go. This is called batch vaporization. The method of drawing off the light ends from the residues in the tank is really partial distillation, and this is known as flash vaporization. And this gives you a different composition, of course, compared with if you evaporate the bulk liquid. Another physical phenomenon that occurs is the actual influence of the heat coming in to the cargo. In large tanks, the heat comes in through the insulation to the surface of the tank, and it causes the liquid to heat up very, very slightly, but that reduces its density so it rises up to the top of the liquid in the tank and forms a warm layer underneath the liquid surface. And this thermal gradient is what actually drives the boiling of the liquid from the tank. So in other words, the heat is conducted around the tank surface and the bulk liquid stays relatively unchanged in temperature. We're talking here probably 1.5 degrees maximum as the temperature gradient of this hot layer, but it certainly drives the boiling that occurs at the liquid surface. Now, this can lead to a very interesting phenomenon which has occurred on a shore tank. It's most unlikely to occur on board a vessel, but we must be aware of it in case we got into this situation. What happened on the shore plant was as follows. The tank was first filled with a light mixture, was actually LNG, and then a heavier grade of LNG from a different source was pumped in, and it, being heavier, lay underneath the light layer. There was really no mixture, almost like oil and water. Now, as the boil-off was drawn away from the light upper layer, it of course became richer in its heavier end, so its density increased, and the lower layer warmed up, its density decreased until at a certain point unstable conditions arose where we had the heavier layer on the top, the lighter layer on the bottom. These spontaneously rolled over and of course caused a massive increase in the rate of evaporation from the tank. It actually lifted the tank roof. Now the tank actually relieved, the roof was designed to relieve in excess pressure, so no mechanical damage occurred, but this was obviously a potentially hazardous situation. It is very unlikely to occur on board a vessel, but procedures may be laid down on board your ship for circulation of the cargo using the cargo pumps to ensure that if you do load cargoes of the same nominal type from different sources, that you do not get into this unstable situation which is known in the industry as rollover. This is why those standards are laid down. And so, to summarize, we can gain a good understanding of the way our cargo system works by a grasp of the basic principles of physics. We need to understand the phases of matter, solid, liquid, and vapor. We need to understand gases and how they behave with pressure and temperature, and the derivation of the general gas equation. We need to realize that the absolute scales of pressure and temperature exist, and these are used in our calculations. We need to understand gas densities and mixing and how these are influenced by composition of the cargoes we're carrying. We need to understand compression, liquefaction, and the fact that a gas will not condense until it is below its critical temperature. We need to understand the basic laws of thermodynamics and how these can be applied to the understanding of the cargo system. Together with the Mollier chart, if we get a sound grasp of the principle of thermodynamics and we understand how the variables, the cargo composition, ambient conditions can affect plant performance, then we can operate our plants successfully and we can carry the cargo safely and professionally.